Hi students, this is Ch1 here. In this video, I'm going to work through Unit 1A, which is Chapter 1 of our textbook. As you watch the video, please take note on the side. You are welcome to print out the PowerPoint. That being said, I still would like you to take note and also mark down any part that you have questions during the video. All right, let's get started. So for Unit 1, again, Unit 1 is Chapter 1. So these are the learning objectives. The main takeaway for the Unit 1 is there are a couple of vocabs and classification that you need to understand. So first of all, what is matter? And matter is broken down into pure substance, which is either element or compound, and then mixture, which is either homogeneous or heterogeneous. Matter can be in these following three states. We'll talk more about that. And also you need to know what is chemical versus physical property and what is physical change versus chemical change. You also need to know how to separate the mixture. In this unit, we learned 3 different methods that you can do, which is filtration, distillation, and chromatography. We also revisit our significant figure and precision versus accuracy. You'll also learn density and how to measure density, and also dimensional analysis. So we'll revisit dimensional analysis. All right, matter. Matter is basically anything that has mass and take up space. For example, your matter, right? The books is a matter, the cell phones is a matter, the electronic device that you're watching this video on is a matter, because it has mass and is take up space. Atoms are basically what make up the matter. Okay, atoms are the things you see on the periodic tables. Chemistry joke, never trust atoms. They make up everything, right? So the makeup part was the one that are maybe not funny. Okay, so matter can be classified as either pure substance or the mixture. When we have pure substance, we have elements or compounds. So let's take a look at that first. Okay, so in the pure substance, like I said, elements. So take a look at the pictures on the bottom: helium, hydrogen, oxygen, phosphorus. These are all elements. They could be together or they could be by themselves. So in this case, you will notice that in each case, there is only one type of atoms, okay? In a compound, there are more than one type of atoms, and they are chemically bonded to each other. They're attached to each other. So for example, our water, it has 2 H's and 1 O. So 2 H are represented by the white circles, and the oxygen is represented by the red circles that you can see in here. All right, moving on. So then we got to understand molecule. So we'll talk about that quite a couple of times in the covalence when I talk about naming, right? So molecules are basically 2 or more atoms joined together chemically. So in this case, you can see in the picture, those are all examples of molecule. The top one are molecule, but they are also known as elements. And the bottoms are molecules, but they are known as compounds, because they have more than one type of atoms. Okay, again, this is in your textbook. Yeah. Checking for understanding. So let's go ahead and go do that. Figure out which one of these are elements, compounds, molecules, or mixture. Okay, mixture just meaning there are multiple elements or multiple compounds mixed together in the picture. So without further ado, I will pause the video so that you can write on it, or you can make note, graph a picture. All right, so the first one is element, right? Hopefully you get that. The second one is a mixture. Okay, I do need to move that thing down. So it is a mixture. In fact, it is made out of elements, and compound, right? It has two different types, okay? This one is still the same. It's a mixture. Again, it has both elements, which is the blue circles, and compound, right? So let me just move things over a little bit so that everything kind of fit in here. Trying to get that in. There you go. All right, so now let's talk about on the bottoms. So how about the bottom one? Okay, so this bottom one is compound because you have two different color atom on it, right? And then we got to the next one. This one is a mixture of elements, right? Because it's only have one sphere, different elements. I will probably put it there. So there's different elements on that one. Same thing as this one. So this is also a mixture of different elements. I'm not gonna write that down. So anyway, so that's what you should have get. All right, moving on. Okay, so two type of mixture out there. So you can kind of see here. The first one is called heterogeneous mixture. And in here, you can kind of see here what heterogeneous look like. Homogeneous mixture, again, this is homogeneous mixture. So pretty much the definition of them is this. Heterogeneous means they are different mixture. So you can see that if you look at the solution, if you look at the mixture, you can tell right away that they are different thing in it. Whether you have homogeneous mixture, if you look at it, the mixture look like the same. Everything look the same, meaning there didn't seem to be a mixture or like different thing in it because they kind of blend together. If you look at it, they look the same. All right, so here is an example of homogeneous mixture. Homogeneous mixture are evenly mixed, uniformly distributed, and visibly indistinguishable, meaning you can't tell, and they have the same property throughout. Okay, so this should be water. I think the picture is too big. So liquid, sugar dissolved in the water. Again, if you drink it, right, you don't know until you drink it because you're looking at it, it's just clear liquid water, right? We could also have a salt solution, same thing. If you dissolve salt in the water, as long as you let it all dissolve, you wouldn't able to tell there is a salt in there, right? So that would be a homogeneous mixture. For example, the air that we're breathing is a homogeneous mixture. It is made out of, besides oxygen, that is mostly nitrogen, right? Oxygens, there's some hydrogen, some carbon dioxide, so various different things. The next one is a solid, or the alloy. Alloy are basically like metal. So for instance, if we're thinking about like rulers or key, right? Everybody have key at home, right? Your house key, your car key, right? So those are the metal part. They are made out of alloy. They are made out of more than one type of alloy. So for instance, we have bronze. Bronze are made out of copper and tin. Brass are made out of copper and zinc. So they're made out of more than two or more metals mixed together. And they look the same because we can't tell, right? The same thing with jewelry. A lot of the jewelry, like for example, gold, they have different percentage of gold versus other chemicals, other metal, right? So that would be an alloy. Homogeneous mixture because we can't tell. All right, so chemical symbols of the elements, compound, and mixture. So you can see here, elements is one capital letter only. You can see that only the first one will have capital letter. The later one are all lower cases. If you have two capital letters or more, you know that means it has more than one element in it. So for example, NaCl, Na is one element, Cl is another element. If you see CuSO4, Cu is one element, S is one element, O is another element. In this case, they're all attached together. There is no space or the plus between them. That means they are chemically bonded together. On the other hand, mixtures will have a plus sign separating them, or they might have AQ, meaning that they are dissolved in the water. So these are all mixture. All right, other chemical symbols such as iron, right? So we have already talked about iron. So you have cation versus anion. Remember what I said, cation is a positive because T look like a plus sign. Anion is a negative. Again, anion, a negative ion. The next case is hydrate. Hydrate are basically water attached to a crystal, solid crystal. So these are like dehydration pack, like a crystal that you put to dissolve moisture, right? So these are the little pack, sometime in like a food that they said do not eat, right? These are there to absorb the moisture so that the food is still crispy or dry. All right. And I do need to talk a little bit about the number there. I make a mistake. The 4 here and then 2 here should be going down. So 2 and 4 has to be subscript. They have to be down there. Let me move it down. The 5 doesn't move down. The 5 is just there. And then the dot is just mean that there's water with it. Okay, so that's what you have to do. And I think there's one more that I need to change. That was earlier. Maybe not. Maybe I have done that. Oh yeah, this one. It's just the grouping. I just need to send it to the back. And then, yeah, there you go. You can see the water now. All right, so let's just continue on with it. So this is how you should write it for the hydrate. All right, so heterogeneous mixtures, these are not uniformly mixed. You can tell definitely there are mixtures such as salad, oils and vinegar, right? Salad dressings, yeah, those are not evenly mixed. Or you can even see, let's say, orange juice, if they have a pulps, they're not evenly mixed, right? They settle down. So yeah. Okay, next one, suspension. These are what is called a type of heterogeneous mixture. We call them suspension. That means when you stir it, they kind of look like uniform, but if you leave it for over time, they separate. They settle down and then they separate into 2 layers. So like muddy water, oils and vinegars, orange juice. Okay, so in the medicine, I have a question is this. Why do many liquid medications say to shake well before using, right? They ask the person to shake well before using. Why is it so? Well, liquid medicines are actually a type of suspension. So you want to mix the chemical evenly for the medicines to be effective. So that's why you have to shake them. All right, this is the classification. So you can see how you can classify them into different things. So first thing you ask for the matter is this uniformly? That means, can you tell there are multiple layer, different things? If you can tell there are multiple layer, different things, it is heterogeneous mixture, right? If it's uniform, that means you cannot tell them apart, like the thing is uniform, that it is homogeneous. Now, the homogeneous could be homogeneous in a mixture, or it is a pure substance. So then you have to think about what is this made out of. Are they all stuck together, or can they be separated apart? If they can be separated apart, then they are homogeneous mixture. If they're all stuck together chemically, then they are pure substance. Then you have to ask, does this has more than one type of atom? Again, type. Right? I didn't say more than one atoms. I said more than one type or more than one kind of atoms. If there's more than one type or more than one kind of atoms, then it is compound. If they are not, then it is elements. Okay, again, this is another pictures. I believe this is from the books. All right, so a type of property of matter, we have physical versus chemical. So let's take a look at them. Physicals are basically things that you can observe without changing it. And it could be intensive or intensive. Let me talk about them. Intensive meaning it doesn't depend on how much you have, such as density, melting point, boiling point, color, hardness, odors, or taste. So what do I mean? Like for example, sugar, okay? Doesn't matter if you have one teeny tiny crystal of sugar or a giant block of sugar, right? The taste of sugar is still gonna be sweet. So that's what I mean by intensive. The next one is melting point. Like for example, ice, water, ice melt at 0 degrees Celsius, water boil at 100 degrees Celsius. So it doesn't matter if you has one small tiny block of ice or a big giant block of ice, it will start melting at 0 degrees Celsius. Density. The density of a substance also doesn't change. We'll talk more about what is density in a little bit. Other stuff, colors, hardness, odor, same thing. Those property doesn't change depending on how much it has. It is always the same, right? So all the water should have the same property, ice water or liquid water, right? Extensive property, extensive. So this is like outside, right? So it's depend on how much it has, such as volume, mass, weight, size. These are all extensive property. So for example, papers, right? So if, you know, this is a sheet of papers, that would be the how much is weight, that will be extensive property. Whether if I rip it up and now it's weight less, right? So that would be extensive property, but it's still a white paper. Doesn't matter if I tore it up, it's still a white sheet of papers. All right, chemical property. Chemical property can only be observed during the chemical reaction. They are ability to burn, ability to rest, ability to decompose, and ability to react with other chemicals. So the chemicals property basically meaning that is the ability for it to go through chemical reaction, right? So ability to change through chemical reaction. So let me talk more about this. Again, these are summary of physical property and chemical property. Notice what chemical property is. It's only happen when they're interacting with other chemicals or if there's some sort of chemical reaction happening. Physical property, you can just observe on its own without having to like react, okay? All right, physical change. Physical change is a change in the substance without changing its identity. So it's basically changing state. So like freezing, melting, condensing, evaporating, and subliming. Other example is also dissolving and breaking and cutting, right? So for example, paper, if I were to tore it into two sheets, right, it's still paper. So that will be physical change. Now, if I were to burn it, now it is no longer a paper, it's gonna become ashes. So that will be a chemical change. All right, take a look at them. Highly recommend you to know the state of matter. For most part, I think everybody know the state of matter. Probably the only part that we probably have a stuck on is this one, sublimations and deposition. So sublime is when solid turn into gas. So that would be like dry ice, right? Go from solid to gas. Deposition is when the gas is coming back to solid. So I think about it as like deposition, right? Deposit, right? Think about it like bank, like you're putting money in, you're depositing. So deposits is like, you know, all of a sudden you get a solid particle show up. So that gas tend to solid, that would be deposition. So again, just a little things to know. Next cases is solid, liquid, gas. You can see here what they are. Yes, the little moving slide underneath the solid liquid gas show you how much energy they have. So you can see here, solid, they do move slightly. They're jiggling, they're moving around. Liquid, they move a little bit more. Gases, they are moving like a little bit all over the place randomly, right? The way I like to make analogy when I was in schools is following. Solid could be like students, like in classroom, in their class, they're sitting on the desk, they are stuck to their desk, kind of, right, stuck. So they kind of move around, right? They will move the papers, they will be writing, right? They might be talking, right? So that would be a solid. Liquid is when the school bell ring and a student left the classroom, but you can see that they're not going random places. They do have an order that they are going through, the direction that they are moving, right? But they are moving. They have a little bit more freedom than the solid, right? And then when I think about gas is like kid in a bounce house, right? They are They have high energy, they're moving around, or kid in the playground, right? They have high energy, they move around, they're knocking into each other, like they're running. So that's what it is, gases. In terms of this, you should know that solid has definite shape and volume. Now you can see here, particles are tightly packed, right? They do move, they are low energy moving, vibrationally liquid. They don't really have a shape because they take the shape of the container. They do have a definite volume though. So you can't just, move container and expect it to fill the container, it won't. Right, they are not very close together, and they actually has a little bit more higher energy. They flow, right, solid. Gases, they don't have a shapes, they don't have a volume, they just kind of fill up the whole entire container, and they are very moving far apart. They have high energy, they move in a random direction. So I like to think about gas as not having volume, like internal, like if we're thinking about like perfumes or like body spray, right? If the students were to spray something in the classroom, like one corner of the classroom, right, soon you can smell it in the whole classroom, right? So that would be like gases. Next one, 3 phases of water. I want you to take a look at it carefully here, right? Solid, liquid, gas. Notice gas they're not stuck together, they are far apart. Looking at solid and liquid, you will see that a little bit confusing for water is happening, right? Water, solids seem to have much more space, like hole in the between, than the liquid water, right? So notice liquid water, they are not really attached to each other, water molecule. Some of them might, but they are not really attached to each other. But in a solid water, they are attached to each other, right? And then this is going to be important. We'll talk more about this. This is something called intermolecular forces. We'll talk more about it. But what I'm trying to show you is this. In the solid water, because of these hole, right, these spaces, the empty spaces, this is why solid water is less dense than the liquid water. This is why ice float, right? So again, this one, I'm not gonna go ahead and write it. This is basically the last few slides that we go over. So go ahead and try to write this out of memory to see if you still remember what we talk about. Okay, so if you have a question, let me know. All right, I'm gonna move on. Okay, so moving on. Chemical change. Chemical change is a change in which a substance is changed into a different substance. So you have changed what it is. So before we go to the next one. So what I'm talking about is, like, think about it, for example, papers, right? If I were to burn it, it is now no longer a paper, it is now ashes. So you can see, again, that would be chemical change. Okay, these are evidence of chemical change. I would say this is important. This slide is important. Please definitely write it down. Remember, memorize this. AP sometimes ask questions about evidence of chemical change. So evidence of chemical change are evolution of gas, which just means it's just forming a gas, right? So if you mix two things, all of a sudden it's bubbling, that would be chemical change. Or it smells different, right? That would be a chemical change. Formation of participants, that's, I'm sorry, not participant, precipitant, right? So that would be precipitate. Yeah, see, I can't say the word correctly anymore. All right, so precipitate, formation of precipitate, that would be like magic, right? So you can see here in the B, the clear liquid is moving into another clear liquid. You might think that is actually not clear liquid. It is. They both are clear liquid, because you can see that from the test tube, it's come out, it's clear. The beaker, majority of liquid are clear, except for where they meet that has this yellow thing coming out of it. So this is a precipitate. So, so yes, that would be like a magic. Right. Next is absorption or release of energy. So in this case, you can see here, it's like, spark, fire, right? That will be a big clue of chemical change taking place. Some of them are not that much. Some of them are much more subtle, you don't really know unless you're paying attention. So for instance, if you have baking soda and vinegar, okay, you might have seen them, you might also see on the video before, like people use these to clean the house around. One of the suggestions, please do not mix baking soda and vinegar, because it makes the thing kind of ineffective cleaning agents because they neutralize each other. Baking soda is a base and vinegar is an acid. If you mix the two together, you will see that bubbles will produce, the gas will produce, and basically they neutralize each other, right? We're gonna get salt and water. We'll talk more about when we talk about acid-base chapter, but if you ever have done it, or you might have done it in a regular chemistry, you might notice that the container where you mix the baking soda and vinegar, they get cooler a little bit. Their temperature drop, so that we know that the chemical reaction taking place. Right, color change is also a chemical reaction. So you can see here, phenolphthalein added to the ammonia dissolving in water, it changed color from the colorless to a pinkish color. Color change is mostly used in titrations and part of the acid-base chapter. Again, that will be like in second semester, we'll revisit some of these ideas. So it's a good idea that you know what is the evidence of chemical change. All right, let's talk about next one. Physical change versus chemical change. So this is the part where I'm talking about a little bit. All right, so chemical change is basically when you're breaking down the glue between the atoms. So in this case, you can see here, water molecule is 2 hydrogen and 1 oxygen, and they're stuck together. So if we kind of break the bond between this hydrogen and oxygen, that would be a chemical change. On the other hand, physical change is basically breaking down these weak interaction between the water molecule. Again, we'll talk more about this in a later chapter. This breaking down weak interaction, that interaction is an intermolecular forces. Yeah. Okay. So different between physical change and chemical change. Again, we will know more about it. I am not really defining intra and intermolecular forces right now. I'm just letting you know what is physical versus chemical change. So in this case, physical change will be breaking down this weak bond, and then chemical change will be breaking down this chemical bond between the elements, between the atoms. Okay, so yes. So the way that you can think about it is this way. If you're breaking down the bond between the atoms, right, in the molecule, that would be chemical change. And if you're breaking down the weak forces between the molecules, again, 2 molecules, not 1 molecule, between the 2 molecules, then it will be a physical change. Okay, moving on. All right, so make sure you can double check what these are for each one. I'm gonna pause for a little bit before I show you guys answers. So let's go ahead and figure out which one it is. Is it physical change or chemical change? All right. Again, I'll go over each one at the end. If you do need to pause it, please pause it in between. All right. All right, so thought I have answer key to this, maybe not. Oh, another thing is you can click on this. This is just fanning comment explaining physical change versus chemical change. I have click on this, so let me actually share a new screen. So that would be physical change, chemical change. Again, I didn't make them. This is someone funny comments about physical change, chemical change. So you can see here. So cutting hair, physical change, bleaching, chemical change, right? So physical change, chemical change, you can see here, right? Again, it's just kind of make it into funny little comment, what it is. So yeah, which of these are physical change or chemical change? Spoiling milk, that is chemical change, and also rusting of the bicycle. Because when the metal are rusting, you're actually reacting with the air, the oxygen in the air. If you break in a glass, it's still glass, right? Except it's a broken piece of glass. Ice cream melting, that's still ice cream, except now it's in puddles, right? That would still be a physical change. So glass and the ice cream, these two are physical change. The other two are chemical change. All right, let's moving back on to our slides. All right, okay. So I guess I haven't not give you the answer to these. So let me just do a quick one. Okay, so answers. Physical change, chemical change, right? The first one's physical, the second one's chemicals. Physicals, again, and then chemical change, because it's reacting and it's turning. Another thing is also adding heat. You can see that for 4 is chemical change, okay? 5, now this one's a little bit tricky. You might think it's chemical change because it's a temperature, but it's actually not. It's just metal just expanding in a heat and then contracted back in a cold. So metal has ability to do that. By the way, this is also how, like, I'm not sure about the new one, but the old thermostats and stuff has the coil, metal coil in it, and then that expand and contracts, and then that's how it works, it functions. So physical change again, and then this is chemical change, color change, right? Physical change, chemical change, and physical change. All right. Okay, now 3 ways to separate the mixtures. This is all utilizing physical change, okay, physical property. Filtration, distillations, and chromatography. So let's talk about filtration. Filtration, you can see here, it's just, you know, if you drink coffee or if your parent drink coffees, and you would have know what is filtration is, right? You're separating, right, the liquid from the solid, and you have a filter paper, right? Although coffee is a little different, but still is filtration, right? Distillations. Distillation is using by the boiling points and is separating the mixture. So the way you can think about distillations is if you ever cook or heat anything hot on a stove and you lift off the lid, right? After you cook, you let it cool down, right? You'll notice that the lid, it has a liquid accumulated in the lid. So this is basically that principles, right? So basically what you do is this, you put the mixture in the here and then you heat it. And then so the one with the lower boiling point is gonna evaporate and then go down. As they go down as a gas, what happened is you're using the water to cool down the gas. So then water condenses back from the gas, right, vapor, to the liquid, and then it's gonna collect it here, right, again. So that's pretty much what it is. Distillations is using and evaporating and then cooling, right? So that's all it's doing. So it must use different boiling points. So for example, if I want to, I could separate the water from the alcohol by using distillation method. That being said, the boiling point or the heat that I added should be, right, the heat of the lowest boiling point substance. Otherwise, it's not gonna work. Okay, the last one is chromatography. Chromatography, if you have ever spilled water on your note, right? If you write with pen, that is, you would have seen chromatography. Chromatography is basically a way for, like, you know, ink and stuff to like smear, right? Because of the liquid. And the reason or the way it is happened is something called polarity, and it's used the polarity to do this. I'm gonna ask you to pause and write it down, the following vocabs about chromatography, so that when I talk about it, you have a little bit more understanding of what they are. So stationary phase, solvents, mobile phase, and then solvent front, right? So make sure you have all that information in there. All right, so let's talk about what it is. So chromatography is a method of separating the mixtures depending on like how strongly they are attached to the mobile phase. So mobile phase is basically the liquid, right? So the liquid in the beaker here is gonna go up the papers, right? Because water and the papers, right? Papers And then usually this is not water. Usually this is like some kind of alcohol there. And then it's gonna be, has a high affinity for paper. So it's gonna go up against the gravity, of course, it's gonna go up. And then as it go up, this color is gonna take a ride with that liquid and it's gonna move up too. Except some of the color would be more attached to the paper. So they kind of either don't move at all or they're gonna move slowly. So that's what it is. Okay, so let's take a look. I would highly recommend you to watch this video. It is called Chromatography, Separation and Purifications video. It is on YouTube's and take note. Okay, so because that's a good job of explaining what to do and what not to do during the chromatography. Okay, so let's do another check for understanding. So when you finish watching this video, you should come back here and try to answer these questions, such as, why don't we use pen or Sharpies to draw a starting line on the paper for chromatography? Right? Why is it important for the solvents to touch the paper but not the starting line? And for this question, assume that solvent is nonpolar and paper is polar. So if you know that anode A travel further than anode B, what can we say about their polarity? Okay. By the way, this is what we're talking about. Solvents, the mobile phase, and then paper, which is the stationary phase. These two are always going to be opposite in polarity. And then the liquid, the ink, or the anode or known substance, right? The one that travels farthest is going to be the one that have highest affinity to the mobile phase or to the solvents phase. So in this case, we said solvents A, anode A is travel further. That means anode A must be the same thing as the solvents or similar to. So that means anode A is probably nonpolar and anode B is probably polar. That's why it's stuck to the paper. Okay. Let's talk about 1 and 2. 1 and 2 all has to do with they interfere with chromatography. Okay, so part 1 is, why don't we use pen or Sharpie to do it? Well, because pen and Sharpie is basically a mixture, right? So what's it gonna do is they also gonna to move up with the solvents or the mobile phase, and we won't be able to tell our anode very clearly. So this is why the line that draw on the chromatography is always pencils, okay, lead pencils, because they won't move with it. They are too big of a particle. Number 2, why is it important that solvents to touch? Well, because the liquid solvents to go up the paper, they need to touch, but the starting line should not touch, because if the starting line were to touch, then what's happened is all the unknown that is on the starting line, instead of going up the paper, is gonna go down the paper and it's gonna dissolve in the liquid or the solvents in this case, and it's gonna make a big mess. Okay, so that's why you shouldn't do that. Okay, another one is RF factor, which is basically measuring how much it moves. So the way it is you do is this, it's really easy. Any RF factor you want to calculate, you are gonna first figure out how much your anode move, and then you're gonna divide it by how much of the solvents moved. It is always, right, or I should say unlikely, that the components or these unknown substance will move the same amount of solvents. Okay, in the rare case, they could move like almost the same, but usually they don't. So you always gonna have like something to calculate. This is called chromatography. So it's kind of like the same idea of separating, but in this case, instead of paper, it is work on the columns, and then column stationary phase actually has a bead with like different like property of attachments or like holes or size. So pretty much depending on what it is, your component is gonna come out at a different time. So this is how you can see here is what happened. Right, so some are more attached to the mobile phase and some are less attached to the mobile phase. So for example, if I were to say this mobile phase is polar, then this green here is a polar, and then this, right, bluish lavender color, it is probably non-polar. Right, again, is whatever the mobile phase polarity, and then you can tell what's going on. Okay, gas chromatography, same idea, what they were trying to do. They always has a mobile phase and stationary phase. You don't have to worry about them. I just put in that here so that you can see. The most common one and the one that we want to care about is the paper chromatography. Accuracy versus precision, you have seen it, right? I'm not gonna say more about this. So pretty much accuracy, you hit the bullseye. Precision meaning all the measurement are the same, like all close by, right? So precision is very important, and I have talked about that before. You know, like they are an ascertaining number. This is why we use suffix and then we use rounding. We have also talked about that one. Okay, this is check for understanding. You should be able to read them and then round them. If you have to pause, go ahead and pause to look, right? So again, what you're gonna do is, remember, you're not recording this top part, you're always recording this bottom part. So always, 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 it is you're looking at the meniscus, okay? Yeah, my line is not really straight, so you want to draw a straight line. So yeah, you want to draw a straight line, always looking straight at the meniscus, right? Again, my line is not very straight. It's kind of hard to draw a line here, but yeah, you want to look at straight, okay? So what pretty much do is 10, so that will be 15, you can count it, 1, 2, 3, 4, 5, 15, 16, and then next is 17, so it's between there. So I will probably say 16.5, you can say 16.4, right? So again, we're guessing. Same thing here, this is 3, this is 4, so that means this is 3.5, and then you can count, right? 6, 7, 8, 9, 10. So that means 3.7, probably closer to 2.8, or maybe you might say is right on the 3.8. Then you can say 3.80. Or you might say, no, it's a little bit above or it's a little bit below. Depending on that, you will say that. Okay. 6 to 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so that's basically halfway is 7, and then after that every point is 0.2. So 1, 2, 3, 4, 5. So that will be a 7, and then 7.2, 7.4, so 7.6, right? So 7.5 probably. So yeah, 7.5 probably sound good, right? So that's what it is. Okay, moving on. Presence error, we'll talk more about it when we start looking at the labs and lab notes, so we're not gonna talk about that one. Suffix, we have talked about them. If you needed to, go back and revisit the significance figure video. Density, same thing, I will look at the density videos and dimensional analysis video. All right, so that's all for chapter 1. If you have any questions, write it down, and then make sure you ask me either in class or later separately by either emailing me or send me through message on Lemay. All right, see you in class.